hello and welcome back to Earth Talks Urban Systems Science Series, our joint Penn State, Morgan State, Johns Hopkins Colloquium Series, sponsored in part by Penn State's Earth and Environmental Systems Institute. I feel like I'm selling a product. Thanks again to Ava Lee, who's in the room here, for helping keep things running. I am pleased today to introduce Dr. Krista Brelsford, a research scientist in the Information Systems and Modeling Group at Los Alamos National Laboratory, that famous place from the movies. Dr. Brelsford was previously the Leanne Russell Fellow at Oak Ridge National Labs and a postdoctoral fellow at the Santa Fe Institute. She earned her PhD from, and we've been doing a study, Krista, of the different degree titles that folks who are speaking bring to the table here. And I think this is actually maybe the most common theme, from the School of Sustainability at Arizona State University. She earned that degree in 2014. And she is going to speak with us today about her research on cities, climate change, and disease. Let's welcome Krista.
Thank you, folks. Thanks for having me. It's a lot of fun to sort of see all the different institutions and how the sort of science of cities has really evolved over the last 15 or so years. So I have always believed that the purpose of science is to do good in the world. And I feel extraordinarily lucky that I get to spend a good portion of my days trying to understand, prevent, and mitigate the biggest risks I see to our global society. That's been climate change, and then also more recently, COVID-19. But how did I get into cities? Well, cities are where most of the people are. And so they're also a lot of where opportunities for influence happen. One way we can think about how cities and human processes fit into our broader understanding of the climate science landscape puts analysis on a scale from sort of global and Earth system focused all the way to hyperlocal and human focused. Models of the Earth system are becoming increasingly finely resolved, and they're now good enough to allow, or even in fact to require, the representation of anthropogenic processes like our infrastructure, our land use, and our land cover. These are the primary mechanisms through which anthropogenic processes influence Earth systems, and they're described on a scale at which we can start to reason about. But when you start to study infrastructure or land use design and management and land use futures, we really quickly realize that the determinant of what infrastructure we might build in cities or across cities is the result of really human-sounding processes, things like demographics, socioeconomics, and resource demands. So we know that human processes are the single largest driver of uncertainty in the future Earth system. This figure from the IPCC shows projected temperature change and uncertainties across some future scenarios of greenhouse gas emissions. It's really clear that uncertainty across these scenarios is much larger than uncertainty within any one of them. And this is the case across geographic scales. One of the biggest uncertainties about coastal wetland loss is, are people going to choose to protect wetlands or not? One of the biggest uncertainties in wildfire risk to humans is how we treat the urban-wildland interface. And one of our biggest uncertainties in urban flood hazards is how we manage water through infrastructure, land cover, and coastal hardening. But most Earth system research so far isn't designed to estimate human-scale consequences. Deborah Cohen here argues that the global models we use to capture planetary scale greenhouse gas effects the planetary scale effects of greenhouse gas emissions don't have the capacity to predict impacts at decision relevant scales. She makes a compelling historical case that this choice was not inevitable, and it's not the only possible strategy for doing climate science research. That's sort of some of what the IFLs are about. Climate research at the scale of decisions and impacts is possible. And I think this perspective is really important because we know that the consequences of climate hazards spread far beyond their direct geographic impact via economic and infrastructural connections. Sugar, Werner, and Sato estimate that the share of damages which are secondary impacts from large hurricanes and cyclones. These are damages triggered by production and supply chain disruptions, rippling across global economic networks. And for the largest storms, these distributed impacts can be 3 times larger than the direct damages. But in order to consider and address risks in their own domain from climate hazards, people need information tailored to their problems and at decision-relevant scales. Cities are a really good laboratory for this. So Simpson et al. Described their framework for addressing cross-system and cross-sector complex climate risks, which build on different ways of characterizing vulnerabilities, hazards, and exposures. And one of the reasons this is important is because every opportunity to address the climate crisis goes through human systems. This is a summary of mitigation opportunities published in the IPCC. This summary is reductive in nature, but it's comprehensive and really unassailable. And one point, as I sort of flash through these graphics, the point that I want you to remember is that blue is stuff that reduces emissions and saves us money under current technology and with current prices. So there's big opportunities for emissions reductions in the energy sector, and in how we manage land, water, and food, and in buildings and infrastructure, and through institutions and social processes. And sort of when you add all of these things up, we can go a long way towards avoiding the worst consequences of the climate crisis with technology that we have today. We have made a good start, and we can do even better. And if the COVID-19 crisis taught us anything, it's that human innovation and a whole of society response can transform our lives on the timescale of days. So back in 2020, each of us participated in the largest collective behavior change that the world has ever seen. Isn't that an incredible thing to be part of? This is a figure showing changes in median travel distance in United States counties in the spring and summer of 2020. You can see in early March when COVID arrived. Of course, it's not when it got here, but it's when we started paying attention. And within a week, half of Americans lived in a county where typical travel distance had fallen by 95%, while 95% of Americans lived in a county where travel distance had fallen by at least half. We've never seen such dramatic behavior change, and it was for our collective good. We can do this. So endogenous analysis of anthropogenic processes is critical for addressing the world's largest problems, both climate change and disease spread. Every mechanism we have for intervention goes through human processes, and a lot of that is in cities. If it's new built infrastructure, new policy, different incentives or punishments, it's all mediated by social processes. And cities are a really excellent laboratory for studying interdependencies between anthropogenic processes and other systems because they act as concentrators of interdependencies across systems. So we can think about urban science questions from multiple different lenses. One lens uses the idea of social scale, right? Just like a tree is distinct from a forest, the processes, drivers, and interactions among people mean that individual choices, community scale processes, and institutions each have unique mechanisms for influencing their broader context. As with geophysical processes, important process interactions and heterogeneities in urban contexts differ across spatial scale from neighborhoods through nations up to the entire planet. Sectors like energy, water, land, or health connect people and resources and act as behavioral aggregators from smaller to larger scales through infrastructure networks and management institutions. And we know that urban systems are embedded within larger environmental systems. They are vulnerable to changing hazards, from geophysical to ecological, which motivates questions regarding resilience and adaptation and provides a lens through which we can understand differential outcomes and interactions across sectors and scales. And then finally, this outer circle highlights the ways that we create knowledge about urban and human systems. Different ways of knowing are possible, and each uniquely contributes to our ability to understand and make sense of complex urban environments. So observation, theory, modeling, co-production, each have unique and important contributions to knowledge. Now, this next set of pictures is a series of cartoons that I drew, highlighting the unique contributions of different academic disciplines for our understanding of cities. So it's not wildly wrong to characterize economists as thinking of cities as a well-mixed bag of interesting people. And often they sort of more or less abstract away the spatial heterogeneity in order to focus on the role of behavior, choices, and policies. Similarly, it's reasonable to consider urban planning as a discipline that views urban locations as a function of interactions, and then more or less abstracts away important heterogeneities in behavior in order to focus on the spatial properties of cities. Engineers focus on the role of infrastructure in defining urban form and function, with the view that above all else, infrastructure defines how people move, interact, and receive services. And then finally, the space of urban complexity sciences has been trying to look for fundamental generalizable properties across all urban sectors, abstracting away many features of each of these many really important features of each of these disciplinary domains. And so these different disciplines have each made really important contributions to understanding cities for different purposes and with different scientific objectives. But one common theme among each of them is that they treat interpersonal interactions as the most fundamental and defining characteristic of cities. And this makes sense, right? Cities exist to enable the circulation of people, goods, and ideas. And in this paper that's still in review, we argue that because this observation has been made by researchers from really different perspectives and with different objectives, it's more likely to be really something that's really fundamental about cities. However, up until recently, actually measuring those interactions at scale has been deeply challenging. We've looked for the signatures of those interactions in many different ways, but a lot of it has been at an aggregate scale, which misses really important heterogeneities in experience and outcome. And so what are the signatures of those interactions across scales and geographies? One way of thinking about how we can start to study these interactions recognizes now that in cities and about human beings, there's all of a sudden a new category of data that we have access to. So COVID-19 specifically, and even more broadly, the increasing digitization of nearly every facet of our lives means that we have information to these ideas, records of digital traces of our choices, our behavior, where we go, that's now sort of being collected by behavioral aggregators or scraping Wikipedia or social media, these kinds of things. And these data complement the rich information that we've historically been able to get from large-scale surveys or case studies. And so they allow pattern detection at qualitatively different scales than was possible before. So in this talk, what I'm going to do is run through a couple of interesting projects thinking across social scales. First, using diphtheria to think from the early 1900s to look at the temporal dynamics of urban disease transmission over the period in which a commercially viable vaccine was introduced. And then using COVID-19 to look at present day interactions between the social process of transmission mitigation and the biologic process of epidemic spread. And then finally, I'll go back to focusing specifically on urban infrastructure. And there, at a city scale, I'll show some strategies for measuring and understanding heterogeneity and inequality in urban infrastructure specifically. Okay, so diphtheria. Diphtheria was a major cause of death in the 19th century, and around the tail end of the 19th century, some antitoxin treatments were invented and their use became really widespread. In this case, I'm using records of urban disease cases to explore a fundamental theory about how cities serve as social reactors, passing along and generating both new ideas and also disease. So the basic idea is very simple. For every doubling of a city's population, a broad suite of aggregate socioeconomic outcomes more than double. They double and add about an extra 15%. And we can see here that many urban socioeconomic characteristics, yeah, if you want the math language, they're well described statistically by a scale-free function of the form shown in this equation here, where beta is the scaling exponent, and it works out to be approximately 7/6. So urban infrastructure scales sublinearly. As the population grows, we need less infrastructure per capita than you might expect from a naive expectation. Socioeconomic characteristics scale superlinearly. We see these kinds of results showing up around the world, from South Africa and Brazil and Europe, and also throughout history, to the extent that we have data that to actually try to measure these things. So the theory underlying these scaling effects is interactions-based, which is exactly the same mechanism for infectious disease. So cities have long been recognized as hotbeds of wealth, crime, and disease. In the story about Dick Whittington and his cat, right, 400 years ago, they thought that London streets were paved with gold. So what we've been hearing about, one way of characterizing urban scaling theory is that scientists have just finally recognized and created a quantitative way to describe the empirical reality in what people have intuitively understood for hundreds of years. Within urban scaling research, there's been relatively little discussion about how urban scaling laws show up in a disease context. Sorry, my office lights turn off when I'm still too still. So one of the things that I did was started looking for data sets of historically important diseases that we now have vaccinations for, because vaccinations should break up the transmission dynamics that cause the urban scaling effect. And so I'm using a data set on diphtheria from the United States between 1916 and 1948 to see how well these theories hold up. This is the total number of diphtheria cases in the study period. And what we have here is a graph where each dot is a United States city. The y-axis is the log of the city's population in some year, and the x-axis is the log of the number of diphtheria cases in that same city. The dashed dot, light blue line, shows the naive expectation that the number of cases increases in direct proportion to the city's population. Or another way of saying this is that you're no more likely to catch diphtheria if you live in a small city compared to a large city. The dark blue line shows the theoretical expectation that there's a 7/6 increasing slope between the log of population and the log of the number of cases. This is saying that if you live in a bigger city, you're substantially more likely to catch diphtheria. And then the black line in the gray area are the best fit estimate and confidence interval from the data that I have available in any given year. Now, before the invention of vaccine, the data is very consistent with the theoretical expectation. It might not perfectly match the 7/6 estimate, but it's clearly superlinear. And then during the 1920s, we invented a commercially viable, shelf-stable vaccine. Diphtheria vaccination became widespread in the 1930s. And then watch how the slope just falls from the superlinear rate down to the naive expectation in just a few years. And then by the 1940s, we can see total disease cases falling all the way until there were 0 cases in the United States in 1948. Now I think this is really neat. The data is perfectly consistent with a theoretical expectation given by urban scaling laws prior to the invention of the diphtheria vaccine, and completely inconsistent after. This is, if you care to know, it's supported by by appropriate statistical tests of the beta coefficients in the pre and post-vaccine period. And this suggests a fundamental change in transmission dynamics of the disease, and that this change happened at the exact same time as we know widespread vaccination began to occur, which is exactly what we'd expect from urban scaling theory. So I think it's pretty cool to both validate urban scaling theory on the one hand, and at the same time, show that these scaling laws can be broken through use of appropriate technology. I could talk about the empirical headaches, but I think I'll just keep moving to go through to give a slightly quicker talk. So we know that COVID-19 supercharged an already profound change in the availability of data about interactions, movement, and behavior. And in this paper, I use COVID-19 as an example of one of 4 case studies in a broader paper which aims to explore and address challenges associated with attributing causality in complex human nature systems. So since March 2020, billions of people worldwide upended their lives in order to fight this virus with the first tool we had, distance. Here's one way of showing that. This is typical travel behavior for each United States county by day starting in early March. Darker green is more travel, lighter green is less. And we can see early on, mobility clicks around like normal. And then on March 12th, every national sports league closed. We all remember this. And over the next 2 weeks, mobility fell to just 10% of normal levels. Mobility really remained quite low through the end of March and into mid-April. And then starting in mid-April, we began to see the safe-at-home policies come into effect. And at the same time, mobility slowly recovered. The policies started to fade in May and June, and by June, typical mobility was about half the pre-pandemic normal. So this figure then is showing logged known cases per capita against the 7-day lag for the mobility index for counties in the United States Northeast for July to September 2020 by county. So based on a model of the biological system alone, we'd expect this line to go up, not down. We know that reducing exposure to people reduces disease incidence. The biological characteristics of this system are really simple. But no amount of statistics is going to make this line positive. And so this figure now shows, the right panel shows the same regression coefficient for a suite of analyses for 4 US regions in the 4 different phases of the disease in between March 2020 and March 2021. And there's wide heterogeneity in the results, but you cannot make the argument that there's a meaningful positive relationship there. In fact, 12 out of the 16 time periods or place time periods have a statistically significant negative association between mobility and cases. So what's going on? People make choices, and these choices are informed by our dynamic understanding of the system that we live in. So we have really good epidemiological models. We don't really necessarily need a pure data science approach to understanding cities. Maybe this is all weird because COVID hit cities first, and maybe something, I don't know. People often are somewhat offended by this figure. And so I have to say, SIR models are absolutely the workhorse of mathematical epidemiology. They are really, really good tools. They're really important. But in December 2021, only about 15% of the United States population had a known infection. A basic SIR model would have predicted a 15% infected rate 16 months earlier by March or April 2020, given what we now know about the original version of COVID. And one of the reasons that we've run into these challenges is that SIR models are tuned for unmitigated disease spread. They fit all of both the biological and the social characteristics of disease response into this beta parameter. And that, well, biology is interesting, and so are our behavioral responses. So one of the things I did was, instead of focusing on unmitigated disease spread, trying to model the interaction of behavior and disease. The Lotka-Volterra model, for the non-ecologists among us, was invented to describe interactions between predators and prey. And it's not actually a terrible way of thinking about interactions between the virus and our attacks on its reproduction. So here in this model, cast mitigation as the predator and the virus as its prey. The math is pretty simple. It's just two ODEs, where in this case, X is COVID cases and Y is our aggregate mitigation effort. Cases grow exponentially and they fall with mitigation effort in cases. Mitigation builds on both itself and overall risk. So if we know that cases are super, super high right now, we might do less risky things. And similarly, if everybody around us is wearing masks and doing all the things, then we might start to do some things too. And then in the absence of new cases, mitigation effort declines exponentially. Those are the only assumptions that go into this. And here we can reduce waves and we can reproduce waves in cases and waves in mitigation, which is what we observe empirically through, nationally, regionally. And then we're also super, super aware of pandemic fatigue, right? Like everybody's tired of COVID now. So one way of building that into our models is making eta and gamma vary with time. And the interpretation of this is allowing changes in mitigation effort to get less sensitive to changes in risk, or let mitigation effort decline more quickly. And with either of those cases, we can see the sort of trends of waves of increasing magnitude that we have observed over the last 4 years. And so this is sort of one strategy for modeling the temporal dynamics of coupled viral and behavioral processes, and the dynamic nature of threat avoidance behavior that we see in our records of human behavior that we have right now might highlight cyclical risk in other social and ecological processes. Flood modelers talk about the sort of memory of exposure to flood and its influence on people's mitigation behaviors. And so I think that sort of this highlights the importance of treating anthropogenic processes as an endogenous part of almost all the systems that we care about. All right, that's the disease section. Now let's swap over to characterization of physical urban infrastructure. Is it typical in these talks to pause for questions, or should I keep on barreling through?
You're welcome to pause for questions if you'd like. Folks haven't done that before, but I don't think it's a bad idea.
Yeah, okay. Do we have questions?
In the room, it's easy for me to see in the room. It's hard for me to
Yeah.
see the chat, but if somebody in the online wants to just pipe up, go ahead.
Yeah, I'm not seeing.
I'll pipe up really quick. Thanks, Chris. I was curious, and I'm sure this is in the papers, which unfortunately I've not read yet. But on the COVID work, you mentioned this question about like, oh, maybe it hit cities first, and so then we're seeing differential relationships of cities versus non-cities. Was it possible to stratify? I mean, do we know if different settlement types showed systematically different patterns in this analysis?
Yeah, so I did do that analysis. It's not detailed in the paper. And I don't have the slides up here I don't have them handy for you. But it is the case that COVID hit cities first, which is sort of what we'd expect from scaling interactions, right? Cities are where all the people are, cities are where even more than all the people are, there's more and more interactions. And so it's easier for a disease to spread in a city, right? That's what diphtheria showed us. It's also interesting, if you plot the Gini coefficient and spatial inequality of cases in sort of that 2020 period, it starts out super, super high, right? Like the first case is the only case, and so the Gini coefficient was 1. And as time went on throughout as COVID sort of rippled across the country, it started in the cities and then it spread, also started in the Northeast and spread to other regions through the country and the world too, although most of my analysis has been US focused. It sort of spread out. But that's not sufficient to, like, I could give you those same sort of negative association between mobility and cases. If I gave you only cities, if I gave you only urban regions, the results are still the same, especially in the sense, like, you get noisier as you cut your data to smaller bits and pieces. But you have to cherry pick your data really, really hard to get the positive association that you would expect from a biological system, from a biological system alone.
Nothing more in the room right here now, Krista.
All right. Then let's talk about built infrastructure. So theoretical strategies like urban scaling theory and the Lotka-Volterra model are cool, right? Like, it's neat to have I think at least, it's neat to have a simple way to describe expectations on a variety of characteristics. But these simplifications and aggregations also miss characterizing important interdependencies, as well as the distributional consequences of urban heterogeneity. So along with population size and density, we really do recognize heterogeneity within cities as one of the fundamental properties of cities. So there's a lot of ways one could characterize urban heterogeneity: income, services, race, ethnicity, culture, business, profession. And this heterogeneity, right, it makes data collection and interpretation more difficult because you have to measure all of the parts of your system, not just the average. And so in a pair of papers on this, what I'm describing here is how we're making progress in just characterizing and measuring heterogeneity in urban infrastructure using examples from Brazil, South Africa, India, and then a little bit work funded by the Southeast Texas Urban IFL within the United States heterogeneity in impervious surface area. So small area statistics for this is sort of one way of looking at population density in Brazil. If the resolution on your screen isn't all that good, all of Brazil looks green, looks like nobody lives in Brazil. We know, of course, that this isn't true. There is extreme heterogeneity in national scale population density in Brazil. Most of Brazil's land area has functionally no one living there, or people living there with a population density less than 50 people per square kilometer. But of course, most of Brazil's population lives in very high population density places. Most Brazilians live in the cities. And so this is population density for Brazil's two largest cities, Sao Paulo and Rio de Janeiro. We can do the same analysis for South Africa and sort of find the same result, that most of South Africa has nobody living in it. Most South Africans live in densely populated areas. Here's some of South Africa's major cities. And again, within city heterogeneity and just straight up population density is really clear. Now thinking about infrastructure instead of just counts of population, one of the reasons that infrastructure is important is that people who live in slums and informal settlements cite infrastructure as one of their central development concerns. Infrastructure access really is central to meeting the UN Sustainable Development Goals. In this paper, we worked together with an organization called Slum and Shack Dwellers International, who has for a long time been collecting neighborhood census-style data of people who live in slums and informal settlements to sort of help us characterize what we know about priorities for people who live in slums and informal settlements. And so we can create a sustainable development index, which is useful for characterizing spatial patterns and infrastructure access across a set of ways of characterizing infrastructure. And so you can collectively refer to these components of our Sustainable Development Index as services. The important point is that the way that we've constructed with this index is that services are they're bounded between 0 and 1. With a value of 0, nobody in this place has access to electricity, sanitation, clean water, any of these individual subcomponents of our overall index. And if the value is 1, then there's universal. Everybody in this place has access to that service. Now there's a big range in quality of life even above 1, right? Like, this index was created to mimic the UN's definition of a slum household. And having basic access to electricity still doesn't mean you can afford to pay for it. But this is sort of the index that we created. And the important point is that our metrics are bounded between 0 and 1, because the math doesn't work out if they're not. So we can measure this, we can measure heterogeneity here within cities. And then within city heterogeneity really is kind of partially masked at the national scale by differences between urban and rural populations. You can see the same feature in a cross-scale analysis of the Gini index for income inequality. But if we want to think about inequality from an infrastructure perspective, where our interesting things are bounded, one thing that's important to sort of remember in your head is that we think about geography in a nested way. The US is made up of states, states are made of counties, counties are cities, cities are made up of neighborhoods. This is the same way that Brazil and South Africa and India have organized their censuses. So we can measure this SDI metric that we've created in every neighborhood. And then within a neighborhood, for neighborhoods within a city, we can find the population weighted mean of the SDI values, and then we can find the population weighted standard deviation of our SDI values. That's pretty easy. That's basic math. And then for any given level of services, there's a limit to how unequal things can be. For example, if all people in the city have complete infrastructure access, there's no inequality. Or if all of your, if all of your people with complete access are concentrated in one neighborhood, or all your people with no access are concentrated in one neighborhood, that's maximally unequal, right? There's nobody in the middle. People are either at 0 or 1. And so we can write down the equation for our maximum inequality. It's just the square, it's right there on the screen, the square root of your average times 1 minus your average. And then we can describe inequality within any given region. It's just the standard deviation over the maximal standard deviation. So one way of looking at this is conditional on your mean value. You have a measured standard deviation. And because our measured things, our services, are bounded between 0 and 1, there's a maximum standard deviation that you can get. And so our inequality or our heterogeneity is just sort of the share of how high you are on this line. So inequality is the ratio between the measured standard deviation and the maximal standard deviation. Towards the upper bounding line here, we've got as much inequality as possible. In the bottom, we've got as equitable of a distribution as possible. So then here, now we're taking data from Brazil and South Africa in around their 2011 censuses, where each dot is a city. They're scaled by the city population. And this is one way of characterizing the relationship between infrastructure access and spatial heterogeneity in that access. So that's sort of a way of measuring infrastructure inequality at the city level, or between cities and neighborhoods, between subplaces and sectors, in any kind of nested geography. And then Bartendu Pandey, who's now at Oak Ridge National Lab, he built on that work for his Yale dissertation. And in this figure, he calculated the average inequality in infrastructure access across South African and Indian municipal regions based on the same metric that we just walked through. And so here, the colors are showing inequality in infrastructure access within different geographies across India or Brazil. And once we have a measure of inequality in access, we can start to characterize it, and we can think about what we can learn from there. So overall, South Africa has higher levels of infrastructure inequality than India, but most especially in rural areas, sorry. And then we can also apply this same construction to looking at heterogeneity in the distribution of impervious surfaces within United States cities. So this is sort of looking across space. This is the same metric. Where here, every little box here is one of the 300 or something United States metropolitan statistical areas. And again, we see we see that heterogeneity in, this is just impervious surfaces, but heterogeneity in impervious surface area varies across space. It varies a little bit within different regions. And then you can, one of the things that sort of I'm working on right now and I'm kind of excited about is looking at how that, because through remote sensing information we can get these data over a longer time series. We can start to look at how this changes across time. So this is now imperviousness data across two different from 2001 to 2021. And for these data, it looks like heterogeneity and imperviousness increases with population, but it seems like it kind of maxes out at something like 60% of the maximum possible heterogeneity. Here, the open dots are 2001 data, and the closed dots are 2021 data. So there's a kind of like, it's kind of like a vector plot of what's happening with imperviousness across different cities. Another way of describing heterogeneity within cities is Moranzai. This is rather than using a hierarchical measure like the inequality measure I just walked you through, this is it's essentially a spatial way of characterizing standard deviation. And when you apply Moranzai to the same population data, we see something that's really interesting here. This is in cross-sectional terms, this is a pretty strong result, right? Like Moranzai, spatial heterogeneity, goes up with population. Okay, we see that here. But when you look intertemporally, it's going down for all of these cities through time. And that to me, that suggests something really interesting, that there are at least two different processes which are driving changes in heterogeneity in impervious surface area within cities. One that's pushing towards an increase in heterogeneity, or an increase in spatial clustering as cities grow larger, and another that's operating through time that's pushing for a decrease in spatial inequality. And I think one sort of exciting opportunity for research in urban systems is trying to figure out what those two different drivers are and how they're each operating in different dimensions. So sort of to summarize, we know that cities are the global locus of both problems and solutions. Cities concentrate interdependencies across systems, and I think one of their most fundamental characteristics is interpersonal interactions. And that infrastructure inequality and heterogeneity is a major characteristic of urbanization. So sort of these are some of the things that we know that we can start to reason about. I think there are processes, generalizable patterns in signatures of how human processes operate at individual city and national scale. And I think that understanding and communicating these patterns, both within scientific communities and to the broader world at large, is one of the most important opportunities that we have for addressing the problems that we face over the next several decades. Yeah, thank you.
Thank you very much. Very interesting talk.
Thank you.
Questions? Anyone have any questions? Krista, I'm going to ask, oh, wait, we have a question in the room. I have a simple question, but this might be a better question.
Great talk. Could you talk a bit more about the significance of impervious surface heterogeneity?
Yeah, so some of it is, I have the data for impervious surfaces, and I'm hoping, and I think one could apply this to access to any bounded measure, right? But with impervious surface area, we have data, and it's potentially useful for some of my colleagues in the Southeast Texas Urban IFL are really focused on flood hazards. And my hope in doing this research is that if I can find a systematic way of characterizing heterogeneity in impervious surface area, then somehow we'll figure out how to tie that into the flood models, because we have existing projections on changes in urban population. If we can characterize heterogeneity in imperviousness, dependent on urban population, then we can say something sensible about how we think the impervious infrastructure of the future might be distributed. And that has the potential to be useful for characterizing flood hazards for cities of the future without, in a way of sort of working around the really challenging problem of what is the urban form of the future. But so many hazards that cities face are dependent on infrastructure. And we don't really have yet a whole lot of good theory on how urban form might evolve over the future.
Other questions? Hang on, I've got another one in the room here.
Definitely enjoyed your talk. Could you talk a little bit more about the science that goes into analyzing the application towards the urban infrastructure?
The science that goes into analyzing the application for urban infrastructure.
Yes.
Thinking about, I'm sorry, could you restate your question? I'm not exactly sure what you're.
I guess
saying.
applying the science towards it is what I mean.
Oh, that sort of, what is this good for? How might an urban planner or somebody who cares about cities
Yes.
make sense of this? Yeah, the science policy gap is a real one, and it's hard, right? And I'm guilty of this. I motivated my talk with, we need to produce decision relevant information. People in cities care a lot about climate change. Urban planners really want to know how to address this crisis that they are going to have to handle. And my sort of theoretical characterization of heterogeneity isn't right now a perfect tool that I can hand over to an urban planner. And that's sort of one of the reasons that I think the DOE urban IFLs, which I think everybody here is pretty familiar with, right? Yeah, okay. I think they're a really important and a really special way that we're funding research right now, because it is one of the first times that the Department of Energy is investing in allowing us time to build relationships between people whose lives and livelihoods and jobs revolve around solving problems for people who live in cities, and folks like me who are used to sitting around in my office with a bunch of data. And so the best case scenario for the work that I'm doing right now, right, is that I come up with an equivalently simple way of saying, this is how we think urban infrastructure will evolve generically in cities over the next 20 to 50 to 100 years. And then this is an instantiation of how we think that process might look like in Beaumont, Texas, in Baltimore, in Chicago. And that's something that urban planners in any particular place, or managers or whomever in any particular place, can use to reason about what kinds of risks they face. Does that make sense?
There's a nod, yes. I'm walking around with a microphone. More questions.
Scans the room. Could I ask a question from over here? Ali, sit back there, is doing work on a bunch of urban optimization modeling to understand inequality associated, or I should say, how to optimize for equity in different kinds of climate adaptation strategies. He's got a model that does that at suburban scale. And what we found recently was that when this model was first written, it was written for the planning district, just kind of like, about a dozen of them or something in Baltimore. And then he reran it for a smaller, more granular neighborhood scale. And it totally changed like the kinds of outcomes you saw with respect to equity. Not just like, where exactly this is, but even the whole nature of the intervention sometimes. I'm just wondering, in your analysis of the Moran's eye, or the other indicators of kind of heterogeneity in these respects at urban scale, have you looked at like what difference it makes, like what you call a neighborhood, like how much you aggregate and how finely you slice the city?
Yeah, it does. I'll see if I can successfully pull up one of my slides. Yeah, right. That like one way of touching at that question, Ben and Ali, is that, the Gini coefficient isn't the metric that I want you to focus on. But yeah, if you look at the same question at different spatial scales, you get really different answers. And that the cause of that is the sort of fundamental heterogeneity that we see in cities. I've done it here for infrastructure, but we know that socioeconomic characteristics are as heterogeneous or possibly more as infrastructural characteristics. And so, yes, both the definition and the scale at which you're looking absolutely can govern your results.
Thank you. I have a really, really simple question while you have this up here. Maybe you said this, but what's the Gini coefficient?
Oh, I'm sorry. The Gini coefficient is a metric that's really commonly used by economists to measure inequality in income. It was sort of developed to measure inequality in income distribution. And so you can imagine if you lined all your people in your population up by wealth, where the poorest are over here and the richest are over here, and your y-axis then would be the share of wealth that's owned by all of the people up to your x-axis value. So, and I might be flipping my orders here because giving this off the cuff is sometimes hard. But so if you have a population of 100 people and a value of $100, and every person has $1, then you're going to get a straight line, right? That is a perfectly equal distribution of your money in your system. But if 99 of your people have no money and one person has $100, then that is a perfectly unequal distribution of value. So the metric itself is the area in between a straight line and your actual measured area, or it's the ratio of the measured area to the whole triangle. But essentially, it's a measure of inequality designed for wealth, but it can be a measure of inequality of any countable thing or any measurable thing, right? And so I've egregiously applied it not to wealth, or in this case, it was on this slide to income, but I talked about applying it to inequality in the distribution of COVID cases, or inequality in access to infrastructure, or sort of whatever you want to measure.
And is 1 perfectly equal or is 0?
0 is perfectly equal. 1
Okay.
is perfectly unequal.
Thank you. Any more questions? Oh, yeah, we have another really simple question in the room here. Moran's eye. Can you give us a quick primer on Moran's eye also?
Yeah, I should have. As I was flipping through my slides, I was like, oh, I should put the equation up, and I ran out of time. So sorry, folks, that is that is me running out of time. Moran's eye is essentially a spatialized way of characterizing standard deviation. Did I put a standard deviation equation in here anywhere? I don't think I did. Sorry.
I think we're okay with standard deviation.
Yeah.
Spatial version, though, if you could
Yeah.
wave your hands at that.
Yeah. So ignoring the sort of normalization stuff, you've got X and Y, or I and J objects in your data set. You've got a mean of your data set. And the Moran's eye is for all the boxes for all the grid cells in your world, for all pairs of boxes I and J, for all the grid cells in your world, I minus the mean, J minus the mean, multiply those. So that becomes something like the square of the difference, but it's the I difference minus the I difference times the J difference, to get the relationship between two grid cells in your world, conditional on them being neighbors, dependent on whatever definition of neighbors you're using. If it's a checkerboard, then you might say I've got this square here, and neighbors are every square that this is touching in a nicely square world. In a non-square world, you have to come up with some mathematical definition of a neighbor. But if all of your neighbors are similar, then your Moran's eye value will be high. If all of your neighbors are dissimilar, like a chessboard, your Moran's eye value will be -1. And so this is a quantitative way of measuring spatial clustering, how similar a place in your spatial world is, how similar that is to its neighbors.
Thank you. Krista, I wanted to try a relatively simple big picture question. This is Ken, by the way, at Penn State. So you started out with your COVID work, and you ended up with, working with I think a differential equation that included human behavior in it, that sort of predator-prey relationship, simple model.
Mhm.
And I note that everything I've heard us discussing in our Baltimore project doesn't yet, and Ben can correct me for sure if I'm wrong, doesn't include differential equations for human behavior. We're more saying, here's choices people would like to make. How do we adapt to those choices? But you're actually driving towards prognostic equations for what people might do. True?
In a perfect world, yes. I mean, I think that we need both. Like, I don't want to say that I absolutely agree that sort of informing people's choices is a deeply important category of research. And also, I think that there do exist, even though we don't have them very well yet, there do exist something like equations about how people behave. There are enough constraints that we all face that are similar, that I think that we can see those at a probabilistic level in aggregate, when we look at large sets of data and large populations of people. This isn't to say that I think we'll ever be able to predict what one person is going to do, but I think we can. I think with the new data that we have, I think we can get there for populations. And if we have those sort of fundamental ways of characterizing human behavior, then we'll be able to more efficiently predict what the future might look like, and that can then inform choices.
Very interesting. I think you're the first speaker in our series to have differential equations for human behavior. That's cool.
If I could comment on that, Ken, we're just chatting in the room here. I think you're right. We don't have that explicitly right now because we don't right now have either an infectious disease dynamics or like an agent-based model or any of those kinds of formulations. What we have is a multi-criteria trade-off analysis optimization algorithm. And so then, therefore, I think human behavior right now would be hidden in our response functions in some ways, because it's not running dynamically. So I think it's a really good point. We need to think about how some of this could be embodied for the problems that need those kind of dynamics. Because as it is right now, I think, right, like Lisa was saying, it was like a choice issue, right? And so, or beyond this stuff on the heat response, it's not a communicable disease, right? It's something where it's just a response, not something that we need that dynamic in there. But in so much in the framing of city heat and other multi-criteria optimization tools to inform adaptation strategy, any of these things could be engaged, but they probably want to emulate them. We want to simplify them into response functions for surfaces that could then be used as a direct policy search function or something like what you would use that statically solves for it as opposed to trying to step it through time.
Neat. That sounds very interesting. I would not want to try to compute it quickly.
Luckily, computers can work for a long time and they work on the weekends.
Yes. Any more questions? All right, looks like we're out in the room at Penn State. Any more from Hopkins or others online? Very good. Let's thank Krista again. They are applauding here, honest.
Yep. Thanks, folks. Thanks for having me.
Thank you very much for speaking. No colloquium next week. It's spring break here. 2 weeks, TC Chakraborty. Thanks a lot.
All right.
Bye-bye.
Bye.
Thanks, Krista. Thanks, everyone.